example 14, this one's a lot more interesting. On the surface, it looks like maybe we should try something like u equals 1 minus x squared. And there's a few other potential options we could have a go at, but I'm just going to start with this and show you why there's a problem with using this as our substitution. So we know we're going to have to get rid of dx as well. So du by dx is going to be minus 2x, which means that dx is going to be du over 2, so 2 du over x, or minus 2d over x. And we have a massive problem now. I can replace my dx, but with something with an x in. And in my integral here, there's no x anywhere to kind of cancel out this one. There is no way of eliminating the x completely with this substitution for u. It just doesn't work. There's no way of doing it. So we need to go back to the drawing board and try and think of another substitution which will work and will somehow get rid of or replace the x with something else. And the clue is here in the answer. The answer is inverse sine. Remember, arc sine means sine inverse of x. And the clue is there in the answer. We've got to use a trig function somehow. And the second clue is to notice that we have 1 minus x squared. And if we have something like 1 minus x squared, well, if this x is, for example, sine of x, or sine of theta, let's say, then this is 1 minus sine squared, and 1 minus sine squared is cos squared. You could also try it with cos. What we'll see is that if you do it with cos, you kind of end up in roughly the same place, but with some negative signs in the wrong location. So the most straightforward way is to replace the x with sine of theta. Now there's something specific and different about this. Theta is not the subject of my substitution anymore. X is the subject. But using this substitution, we can replace our x's with stuff in terms of theta, with a bunch of trig functions. So let's just look at how that works. First of all, dx by d theta is going to be cos theta. So what that tells me is that dx is the same as cos theta d theta, and x is equal to sine theta. So my integral now looks like 1 over the square root of 1 minus sine squared theta multiplied by cos theta d theta. So I've successfully gotten rid of all the x's. I've only got thetas in here. But the reason this is such a good substitution is that I can go a step further. 1 minus sine squared is cos squared. So this is 1 over the square root of cos squared theta multiplied by cos theta d theta. And what is the square root of cos squared? Well, it's just cos. So this is the integral of 1 over cos theta multiplied by cos theta d theta. And lo and behold, well, that means that this is just the integral of 1 with respect to theta. So it's an incredibly simple result, especially when you look at just how complicated the thing looks in the first place. You know, we began with 1 over a root of 1 minus x squared, and now we just have 1. We need to finish the job, of course. We need to get to the end of this process. So if we integrate 1, then what we get is theta. So this equals theta, which is not a problem at all, plus some constant. And we need to remember that we said in the beginning x equals sine theta. So that means theta is the inverse sine of x. So this is equal to inverse sine x plus c, and what it says in the textbook and what we often see written by hand is arc sine x plus c. Remember that the reason we see arcsine x is because we don't have this -1 notation, which is in some situations quite confusing because it does not mean the same thing as to the power of -1. So there we have it. This is a bit of an odd one. You wouldn't necessarily guess that our substitution here is sine theta, but there is this clue in the answer being a trig function. And this is one of these things where experience is what really matters. If you've seen a few where this is what you do, then it might just trigger a memory when you spot these and go, oh yes, I think that's what I need to do. Let's have a go at that.